From the moment we open our eyes and stretch our arms into the space around us, we are immersed in a world that seems simple and obvious. We move forward, backward, left, right, up, and down. These directions feel so natural that we rarely pause to consider what they really mean. Yet beneath this everyday experience lies one of the most fundamental concepts in all of mathematics and physics: the idea of dimensions. A dimension is not a physical object, but a way of describing how something can extend, how it can be measured, and how it can be located in space. When a child draws a line on paper, the pencil moves in only one direction, creating a mark that has length but nothing else. This is what mathematicians call one dimension. Add another independent direction, and suddenly the line can form a square, a triangle, or any flat shape. This is two dimensions, the realm of surfaces, of paper, of maps. Add yet another direction, one that lifts shapes out of the page, and you enter the three-dimensional space we inhabit. Now the square can become a cube, the triangle can become a pyramid, and the circle can become a sphere. The language we use to describe these extensions is rooted in geometry. The ancient Greek thinker Euclid described points, lines, and planes, establishing rules that guided mathematical thought for over 2,000 years. His system, known as Euclidean geometry, assumes a flat and infinite space, one where parallel lines never meet, and the shortest path between 2 points is always a straight line. Centuries later, René Descartes introduced a tool that remains central to how we picture dimensions today: the Cartesian coordinate system. By assigning every point in space a set of numbers corresponding to its distance along each axis, Descartes gave us a precise way to locate anything within a dimensional framework. This grid-like picture of space became so deeply embedded in science that it feels inseparable from reality itself. When you tell someone to meet you at the corner of one street and another, you are relying on a two-dimensional coordinate system. When a pilot navigates an aircraft, they must think in three coordinates: latitude, longitude, and altitude. Without this geometric framework, modern technology from computer graphics to satellite navigation could not exist. Yet the story of dimensions is not only a tale of mathematics, it is also the story of why life, as we know it, exists at all. Imagine, for a moment, a universe with only two dimensions. Living beings would have no thickness, existing like figures drawn on a page. Any internal organs would be exposed if another shape passed by, cutting across their bodies. The stability of structures would be impossible. Proteins could not fold, cells could not form, and complexity could never arise. A two-dimensional universe would be too fragile to host life. Now imagine a universe with 4 spatial dimensions instead of 3. At first, this might sound like an expansion, as if life could simply take advantage of an extra direction. But the mathematics shows otherwise. The forces that hold our universe together, especially gravity and electromagnetism, behave differently depending on the number of dimensions. In more than 3 spatial dimensions, gravity weakens too quickly with distance. Stable planetary orbits, the kind that allow worlds to circle stars without collapsing into them or drifting away, would be impossible. Chemistry, too, would fail to resemble anything familiar. The delicate balance that allows atoms to form molecules and molecules to form living organisms depends on the 3-dimensional structure of space. Add or subtract a dimension, and the very fabric of life unravels. This realization is striking. The number 3, which seems so simple, is not arbitrary. It is a prerequisite for stability, for complexity, and ultimately for consciousness. When physicists and mathematicians study the rules of higher dimensions, they often find that 3 stands out as special. In 3 dimensions, gravity allows orbits to remain stable over billions of years. In 3 dimensions, chemistry permits the richness of carbon, water, and DNA. In 3 dimensions, geometry supports the architecture of galaxies and the spiral of a seashell alike. As we walk through a forest, climb a mountain, or watch clouds drift across the sky, we seldom think of ourselves as inhabitants of a mathematical structure. Yet everything we see and touch is bound to the framework of length, width, and height. Every tree has a trunk with diameter and height, Every bird spreads wings that beat through space, and every star shines as a sphere suspended in the night sky. The fabric of our experience is inseparable from the three-dimensional stage on which it unfolds. Still, while three dimensions define our lives, mathematics does not stop at three. In equations and abstractions, there is no reason to halt the counting at the number that suits our perception. A line can be extended to a plane to a cube, and a cube to something beyond, something that defies visualization, yet remains perfectly consistent within mathematics. Our familiar world is only one case in a vast spectrum of possibilities. The very act of stepping beyond three dimensions challenges us to expand imagination beyond what eyes can see. The human mind evolved to navigate forests and rivers, not to picture a four-dimensional cube. Yet mathematics gives us tools to glimpse the logic of higher spaces, even if direct perception is forever out of reach. And so, as we close our reflection on the necessity of three, we must open the door to the question of what lies beyond. Three is familiar, but mathematics has never stopped counting there. The three dimensions we experience are not simply a convenience for human thought, they are woven into the very physics that govern the universe. To see why, it helps to consider how physical laws depend on dimensionality. The law of gravity, first written clearly by Isaac Newton in the 17th century, describes how two masses attract each other. In our three-dimensional world, the strength of that attraction decreases as the square of the distance between them. This inverse square law is not an arbitrary formula. It arises from the way force spreads through space. Imagine the gravitational influence of a planet radiating outward like light from a lamp. The farther you move from the source, the more that influence is spread across the growing surface of an imaginary sphere surrounding it. Because the surface area of a sphere increases with the square of its radius, the force must decrease with the square of distance. This reasoning shows why dimensions matter. If space had only two dimensions, gravity would diminish more slowly, weakening in proportion to distance itself, rather than distance squared. In such a universe, celestial mechanics would be radically different. Orbits might not be closed paths at all, but spirals that either collapse into the central body or drift endlessly outward. With four or more spatial dimensions, the reverse problem occurs. The surface of a higher dimensional sphere grows more quickly with distance, which means gravitational strength would fade too rapidly. In those cases, stable orbits cannot exist. Planets would not circle stars in predictable patterns. Solar systems would not last long enough for life to emerge. The same pattern holds for other fundamental forces. The electromagnetic force that binds electrons to nuclei and allows atoms to form follows the same inverse square law in three dimensions. Alter the number of dimensions, and the balance of attraction and repulsion that makes chemistry possible falls apart. In two dimensions, atoms could not form complex bonds. In more than three, the binding of electrons becomes unstable. The beautiful variety of molecules that enables proteins, DNA, and ultimately living cells depends directly on three-dimensional laws. This is not speculation, but rigorous analysis. Physicists, such as Paul Ehrenfest, in the early 20th century, examined what the laws of physics would look like in universes of different dimensionality. His conclusion was clear: three spatial dimensions are uniquely suited to allow stable structures, both on astronomical scales and on the microscopic scales of chemistry. This does not prove that no other kind of universe is possible, but it shows why our particular universe is compatible with life. Even the way light travels reflects the dimensional structure of space. Light radiates outward in spherical waves, its intensity diminishing with distance squared. This is the same geometric principle that governs gravity. If dimensions were different, the spreading of light would also change, altering the possibility of vision, photosynthesis, and energy exchange. The simple act of seeing relies on three dimensions. Beyond the physics, the geometry of three dimensions shapes how organisms evolve and interact. Consider breathing. In three dimensions, lungs can branch into complex networks of airways that maximize surface area relative to volume, allowing efficient gas exchange. In two dimensions, such branching would be limited to flat patterns, incapable of supporting large or active creatures. In more than 3, the efficiency of diffusion would not scale in the same way, altering the relationship between surface and volume. Evolution, as we know it, depends on this delicate balance. The structure of DNA itself is another reminder of how 3-dimensional geometry sustains life. The double helix relies on precise spatial orientation of molecules. The twisting ladder of base pairs can only maintain stability within a 3-dimensional framework. The chemistry of hydrogen bonds and the packing of chromosomes in cell nuclei both rely on space being exactly 3-dimensional. Alter that framework, and the molecules central to heredity and biology may not exist at all. We often imagine that if there were an extra dimension, life might simply adapt. Yet the mathematical analysis shows that adaptation would not be possible in the same sense. The forces and bonds that make life possible would not form in the first place. What feels to us like a neutral backdrop, 3-dimensional space, is in fact a fundamental precondition for everything we know. Still, it is important to recognize that mathematics can describe spaces of any dimension. When mathematicians study equations, they can extend the rules of geometry beyond 3 without contradiction. In those realms, 4, 5, or even 100 dimensions can exist as abstract constructs. The challenge lies in distinguishing between what is mathematically permissible and what is physically real. For everyday life, the physical laws of our universe confine us to 3 spatial dimensions. Yet even within this limit, the human imagination has always tried to stretch beyond. Ancient philosophers pondered whether the geometry of space was infinite or finite, whether it curved or remained flat. The work of Euclid seemed to settle the matter, but later, mathematicians began to explore alternatives. By the 19th century, Carl Friedrich Gauss and Bernhard Riemann were developing new forms of geometry that did not rely on flat space at all. Their work would eventually provide the foundation for modern physics. But long before that, the 3-dimensional world remained the stage upon which all natural processes played out. The ordinary activities of human beings testify constantly to this structure. Building a house requires measuring length, width, and height. Sailing a ship requires navigating latitude, longitude, and depth. Even in language, metaphors of dimension are everywhere. We speak of deep emotions, high hopes, and broad horizons. The human experience is inseparable from 3 dimensions. To live in 3 dimensions is to exist within a set of rules that quietly dictate what is possible. They determine the shape of galaxies and the shape of our lungs, the orbit of planets and the orbit of electrons. They determine whether life can arise and whether it can endure. These rules are not chosen by us but given, and they remind us that reality is structured in ways that are both limiting and profoundly enabling. And yet, as much as 3 dimensions define existence, they do not limit the human mind. Mathematics whispers that more is possible, that other dimensions can be imagined, if not directly experienced. The tension between lived reality and mathematical possibility has been one of the most fertile sources of discovery in the history of science. It is in this tension that we begin to sense the leap awaiting us beyond the familiar. To grasp the uniqueness of our 3-dimensional world, it is useful to imagine how perception itself would change in a universe of different dimensionality. Vision is one of the clearest examples. In 2 dimensions, organisms could only see shapes on a plane. There would be no depth, no distance behind or in front, only the shifting outlines of neighbors as they slid across a flat surface. Hiding behind another object would mean vanishing completely from view, because there would be no way for light to curve around and reveal edges. The richness of perspective, the ability to gauge distances and navigate through space, would be absent. In more than 3 dimensions, vision becomes even harder to imagine. Light would still spread, but the geometry of shadows and surfaces would no longer resemble anything familiar. The brain, which relies on depth cues shaped by 3-dimensional geometry, could not function in the same way. Even sound, another sense we take for granted, depends on 3 dimensions. The vibrations of air that carry voices and music spread out spherically. The strength of those waves fades according to the same inverse square rule that governs light and gravity. In a universe with different dimensionality, sound would carry differently. In 2 dimensions, it would not radiate through open air, but only along surfaces, like ripples on a pond. In more than 3, it would weaken too quickly to travel far. Communication itself would be transformed, perhaps rendered impossible at any meaningful distance. The stability of matter offers another striking reminder of dimensional necessity. Atoms rely on quantum mechanics, the set of principles governing particles at the smallest scales. The energy levels of electrons around a nucleus are solutions to the Schrödinger equation, which depends explicitly on the number of spatial dimensions. In 3 dimensions, these solutions allow discrete, stable orbits that prevent electrons from crashing into nuclei. If space had 4 or more dimensions, these solutions do not behave the same way. Electrons could not settle into stable configurations, meaning atoms would not exist. Without atoms, there would be no chemistry, no molecules, no stars, and no life. This is not a matter of convenience, but a matter of mathematical inevitability. The cosmological consequences are just as profound. Stars shine by fusing hydrogen into helium, a process that requires delicate balances of pressure, gravity, and nuclear forces. The geometry of space influences how stars form, how they burn, and how they die. In universes with different numbers of dimensions, stellar evolution might not be possible at all. The periodic table, the foundation of all chemistry, is not a universal truth that would appear everywhere. It is the outcome of quantum mechanics operating specifically within 3 dimensions. It is worth pausing to consider what this means for our place in the cosmos. The laws of nature are not written for us, yet they happen to align in such a way that life can emerge. This observation has been described as a kind of selection effect. We find ourselves in a 3-dimensional universe, not because other dimensionalities are impossible in mathematics, but because 3 dimensions provide the conditions in which observers like us can exist. If the universe were otherwise, there would simply be no one here to ask the question. For centuries, human beings assumed that the geometry of space was obvious. Parallel lines never meet, triangles add to 180 degrees, and cubes have 6 faces. But as the 19th century unfolded, new insights began to show that even geometry could be richer than expected. Mathematicians discovered consistent systems in which Euclid's rules did not apply. Space could curve, stretch, and twist in ways previously unimagined. These ideas would eventually prepare the ground for Einstein's theory of relativity. Yet even as geometry expanded into new realms, the essential fact of 3 dimensions remained. The canvas might bend, but the number of directions in which it could extend stayed fixed. Our everyday lives continue to mask the strangeness of this fact. When you stack books on a shelf, you do not marvel at the possibility of arranging them along 3 axes. When you fill a glass with water, you do not reflect on the fact that volume itself is a 3-dimensional measure, length times width times height. And yet, each of these acts is only possible because of the dimensional structure of reality. Behind every ordinary gesture lies the quiet architecture of the cosmos. To live in 3 dimensions is to live within boundaries that are both restrictive and fertile. They restrict us because we cannot step sideways into another direction beyond length, width, and height. But they are fertile because they allow complexity, growth, and thought to flourish. Planets trace arcs around stars, galaxies weave spirals through space, and organisms evolve intricate structures, all because the geometry of 3 dimensions makes such order possible. The familiarity of 3 dimensions can easily deceive us into thinking it is the only possibility, but mathematics reveals that it is one among countless options, a special case in a much broader spectrum of dimensionalities. To appreciate 3 is to recognize both its necessity and its contingency. It did not have to be this way in the abstract, but it is this way in the real universe we inhabit. And so we close the first stage of our journey. We began by examining how dimensions define our experience and why 3 in particular is essential for the stability of physics, chemistry, and life. We saw how geometry, physics, and biology all converge on the conclusion that 3 dimensions are uniquely suited for complexity. We recognize that everyday actions, from seeing to breathing, are bound to this framework. Yet as complete as 3 dimensions may seem, mathematics beckons us further. It insists that the counting does not stop here, that beyond the space we inhabit lies a realm of higher dimensions, waiting to be explored. The familiar is only the beginning. Mathematics has never stopped at 3. In the 19th century, mathematics underwent a transformation that forever changed how people thought about space. For more than 2 millennia, Euclidean geometry had seemed unshakable. The rules laid down in ancient Greece appeared universal, describing lines, planes, and solids in 3-dimensional space with perfect clarity. Yet slowly, new questions began to emerge. Could there be other kinds of geometry, ones not bound to the flat surfaces and straight lines of Euclid? Could mathematics reach into dimensions beyond the 3 that our senses reveal? The seeds of this revolution were planted by thinkers like Carl Friedrich Gauss, who studied the curvature of surfaces and realized that geometry did not always have to be flat. A sphere, for example, is a curved 2-dimensional surface. On such a surface, the sum of the angles of a triangle does not equal 180 degrees, as Euclid had declared, but more. Similarly, on a saddle-shaped surface, the sum is less. Gauss demonstrated that this curvature could be measured entirely within the surface itself, without reference to a surrounding space. This insight opened the door to a new way of thinking about dimensions. If 2-dimensional geometry could bend and twist, why should 3 dimensions be fixed and absolute? Bernhard Riemann, a student of Gauss, carried these ideas even further. In his groundbreaking lecture in 1854, he introduced the concept of manifolds, mathematical spaces that could exist in any number of dimensions, each with its own kind of curvature. Riemann showed that the familiar rules of geometry were just one possibility among many. By altering the underlying assumptions, one could imagine spaces of 4, 5, or even infinitely many dimensions. These higher dimensional spaces could not be pictured directly, but they could be described rigorously, using equations and coordinates. Riemann's ideas were so profound that they eventually provided the framework for Einstein's theory of general relativity, though that would not come until the early 20th century. In the same era, mathematicians also began to explore the possibility of visualizing higher dimensions through projections and analogies. Just as a 3-dimensional cube can be represented on paper by drawing its edges in perspective, a 4-dimensional cube, known as a tesseract, can be represented in 3 dimensions through projections. This does not allow us to see the 4th dimension directly, but it gives a glimpse of how such a structure might behave. Cross-sections provide another tool. A sphere passing through a 2-dimensional plane appears to flatland creatures as a series of circles that grow and shrink. By analogy, a 4-dimensional object intersecting our 3-dimensional space would appear as a series of changing shapes, bewildering but consistent. The expansion of mathematics into higher dimensions was not limited to abstract geometry. It found practical uses in unexpected places. In physics, the language of higher dimensions allowed theorists to formulate more general equations, even if those dimensions could not be observed. In data analysis, the concept of an n-dimensional space provided a natural way to represent variables. Each data point could be thought of as a position in a space where each axis corresponded to a different feature. As statistics evolved into modern machine learning, these high-dimensional spaces became central. Algorithms that classify images or recognize speech operate in spaces with hundreds or even thousands of dimensions, treating each pixel or frequency as a coordinate. Though we cannot picture such spaces, mathematics handles them with ease. Even in everyday life, traces of this high-dimensional thinking appear. Consider the economy of a country. It cannot be described by a single number, such as gross domestic product, alone. To understand it, one must consider many variables, such as employment rates, inflation, trade balances, and technological innovation. Each of these adds a dimension to the space in which the economy lives. The economy is not literally existing in higher physical dimensions, but the mathematical model of it requires a high-dimensional framework. The leap to higher dimensions thus became a bridge between pure mathematics and practical application. What once seemed like an abstract curiosity soon became a language for describing real problems. The elegance of this mathematical expansion lies in its universality. Whether in geometry, physics, or data science, the rules of higher dimensions follow consistently from the foundations laid by Gauss and Riemann. Yet even as mathematics proved that higher dimensions were not only possible but useful, a deeper question remained. Are these dimensions only mental constructs, tools of calculation, or do they correspond to something in physical reality? The answer would not come quickly. For decades, higher dimensions remained a mathematical playground, admired for its beauty, but not tied to observation. It would take the revolutions of physics in the 20th century to bring the possibility of real extra dimensions into the realm of science. The 19th century, then, marks the moment when human thought broke free of the prison of three-dimensional intuition. Mathematicians dared to imagine spaces beyond the visible, guided not by sight, but by logic. The leap was not easy, for the human mind resists visualizing what it cannot perceive. But the symbols of mathematics have no such limit. They can extend as far as imagination demands. And once the leap is made, there is no turning back. The world of three dimensions may be the one we live in, but the world of higher dimensions is the one mathematics invites us to explore. Three dimensions, so stable and familiar, are no longer the boundary of thought. They are the foundation on which vast new structures can be built, spaces of any number of dimensions waiting to be mapped. And if mathematics can describe them with precision, the question that follows is inescapable. Could nature itself make use of these higher dimensions, hiding them in ways we have not yet learned to see? The journey into higher dimensions during the 19th century was not confined to the ivory towers of mathematics. It also entered the imagination of writers, educators, and philosophers who sought to bridge the gap between abstract theory and human understanding. One of the clearest tools for doing this was analogy. To explain four-dimensional space to people accustomed only to three, thinkers often used the example of lowering a dimension. Just as a cube is to a square what a square is to a line, a four-dimensional hypercube, or tesseract, is to a cube. By stacking these analogies, one can build an intuitive ladder up to higher dimensions. This ladder of analogy became a central way of teaching ideas that otherwise resist visualization. Consider the shadow of a three-dimensional object cast on a wall. A sphere projects as a circle, a cube as a square with lines connecting corners. These shadows do not fully capture the object, but they convey hints of its form. In the same way, a four-dimensional object projected into three dimensions would appear as a distorted, changing shadow, a lower-dimensional echo of its higher dimensional structure. Though no one can directly see such an object, the mathematics of projection gives it consistency. Mathematicians developed techniques to study these higher dimensional forms systematically. They extended the definitions of familiar shapes into additional dimensions. A triangle becomes a tetrahedron in three dimensions, and in four dimensions, the analog is called a simplex, a structure with 4 points connected in the most basic way. A cube extends to a hypercube, and a sphere extends to a hypersphere. Each new dimension adds a twist to properties like surface area and volume. For example, the volume of a hypersphere grows in unusual ways as the number of dimensions increases. This discovery was not just a curiosity. It became deeply relevant in probability theory and statistics, where high-dimensional spaces govern how distributions behave. The practical value of these mathematical tools grew rapidly. In physics, higher dimensional geometry offered ways to represent more complex systems. A gas of particles, for instance, can be described by assigning each particle both a position and a velocity. Together, these form a phase space with 6 dimensions, 3 for position and 3 for momentum. The system evolves through this higher dimensional space, and its behavior can be studied using geometry that goes beyond ordinary three-dimensional intuition. Without the language of higher dimensions, the statistical mechanics that underpins thermodynamics would not be possible. Another striking example lies in the study of vibrations and waves. The motion of a string can be described as a point moving in a high-dimensional space. each dimension corresponding to a possible mode of vibration. This high-dimensional representation makes it possible to analyze sound, light, and even quantum states. Here again, the mathematics of higher dimensions proves indispensable, even though the physical world around us appears confined to three. The emergence of higher dimensional geometry also reshaped the philosophy of science. Henri Poincaré, a French mathematician and philosopher, reflected on whether space was truly three-dimensional, by necessity, or whether it could be otherwise. He argued that our perception of three dimensions might be shaped as much by the limitations of our senses as by the structure of reality. Poincaré's writings influenced both mathematicians and philosophers to consider the possibility that human cognition sees only part of the picture. Perhaps nature's true dimensionality is richer than what we can directly observe. At the same time, popular culture began to absorb these ideas. The notion of hyperspace, though not rigorously defined, entered literature as a metaphor for travel beyond normal limits. Visual artists experimented with representations of four-dimensional objects, creating drawings that hinted at forms beyond the visible. These cultural explorations reflected the same fascination that drove mathematicians, a fascination with the possibility of more than three. Yet for all the imaginative excitement, the mathematical leap remained anchored in rigorous reasoning. Riemann's generalization of geometry provided the rules. Every space, no matter how many dimensions it contained, could be described by a metric, a function that defined distances between points. This simple concept allowed mathematicians to extend the core ideas of geometry endlessly. Spaces could be flat or curved, compact or infinite, continuous or discrete. The number of dimensions was simply a parameter that could be increased without limit. The beauty of this discovery lies in its universality. Once you accept that distance can be defined by a rule and that coordinates can be assigned to points, the rest follows naturally. Whether the space has 2, 3, or 1,000 dimensions makes little difference to the logic. Geometry becomes a language that scales effortlessly upward. This universality explains why high-dimensional spaces became so useful in fields as diverse as physics, statistics, and computer science. By the late 19th century, the concept of higher dimensions had become firmly established in mathematics. It was no longer a question of whether such spaces could be described, but how they might be applied. This shift marked a profound change in the history of science. Before, dimensions were considered part of physical reality, fixed and given. After, they became part of a mathematical toolkit, expandable and adaptable as needed. Still, an important gap remained. Mathematics could describe higher dimensions with ease, but no experiment had ever shown them to exist in the physical universe. The leap was complete in the realm of thought, but it had yet to cross into the realm of observation. The stage was set for the 20th century, when the merger of mathematics and physics would reveal that at least one more dimension, time itself, was inseparably linked to space. The fascination with higher dimensions in the 19th century also reshaped how people thought about the limits of human imagination. For thousands of years, geometry had been tied closely to sight and touch. A line could be traced with a finger, a triangle drawn on parchment, a cube carved from stone. These shapes belonged to the visible and tangible world. But as soon as mathematicians began extending geometry into 4 and higher dimensions, they stepped into a realm that could no longer be pictured directly. It required trust in symbols and logic over intuition. This challenge led to both excitement and discomfort. Some thinkers embraced the new mathematics as a natural extension of human reason, while others resisted, arguing that dimensions beyond 3 were meaningless since they could not be seen. The debates highlighted a tension that still exists today, the tension between what mathematics allows and what the senses confirm. Yet time and again, mathematics has shown its power to reach truths about nature long before experiments catch up. The later success of Einstein's relativity, which relied on Riemann's higher dimensional geometry, would vindicate this faith in abstract reasoning. Even without direct physical application at first, the exploration of higher dimensions yielded insights into problems that seemed unrelated. In statistics, for instance, the concept of multidimensional spaces became essential for analyzing probabilities. The Gaussian distribution, so central to data analysis, behaves differently in high-dimensional spaces. As the number of dimensions increases, counterintuitive effects emerge, such as the concentration of probability near the edges of a region rather than its center. These effects, far from being curiosities, underpin the mathematics of sampling, error analysis, and modern algorithms. In computer science, which was just beginning to emerge at the end of the 19th century and would flourish in the 20th, higher dimensional mathematics provided the framework for organizing and processing information. A dataset with many variables is naturally represented as points in a high-dimensional space. Patterns and clusters that cannot be seen in raw data become visible when analyzed geometrically. This idea forms the basis of machine learning, where algorithms navigate high-dimensional landscapes to classify, predict, and recognize patterns. Every time an image recognition system distinguishes a cat from a dog, or a speech recognition system transcribes a voice into text, it is operating in a space of hundreds or thousands of dimensions. The legacy of the 19th century's leap into higher geometry lives on in the technologies we use daily. In physics, the mathematical tools of higher dimensions became essential long before extra dimensions were considered as part of reality. The phase spaces of classical mechanics, the state spaces of thermodynamics, and the Hilbert spaces of quantum mechanics all make use of higher dimensional structures. None of these spaces are physical in the sense of being additional directions one can walk through, but they are indispensable mathematical arenas in which the laws of nature play out. This blurring of the line between abstract dimension and physical reality set the stage for deeper questions. If higher dimensions are already so effective in describing the universe mathematically, might they also exist physically? This question, though not yet answerable in the 19th century, hovered in the background of scientific thought. Writers and educators sensed the cultural power of the idea. Edwin Abbott's book Flatland, published in 1884, used the story of a two-dimensional world to illustrate how limited perception can be. When a three-dimensional sphere visits Flatland, the inhabitants see only slices of it, first a point, then a growing circle, then a shrinking one. The story was intended as a satire of social hierarchies, but it also became a powerful metaphor for the challenge of imagining higher dimensions. To this day, Flatland remains a gateway for students encountering the concept for the first time. Through such metaphors, the idea of higher dimensions moved from the realm of specialist mathematics into the broader culture. It suggested that reality might hold surprises far beyond what eyes can see. At the same time, it emphasized humility. Just as Flatland's inhabitants could not comprehend three dimensions, perhaps we, confined to three spatial directions, cannot fully grasp higher ones. The 19th century thus gave not only new mathematics but also a new philosophical lens on human limitations. As the century drew to a close, the mathematical leap to higher dimensions had achieved two things. First, it had established rigorous frameworks for describing spaces of any dimensionality, complete with tools for measuring distance, curvature, and volume. Second, it had spread the notion of higher dimensions into scientific, philosophical, and cultural discourse, planting seeds that would later flourish in physics. The leap was real and irreversible. Once mathematics revealed that dimensions were not fixed at 3, the mind could never again assume that 3 was the final word. The implications were profound. Mathematics had shown that higher dimensions could be defined consistently and applied usefully. The imagination had begun to adapt, guided by analogies and projections. Yet the question remained unresolved. Were higher dimensions only a language of thought, or were they part of the fabric of nature? The answer would begin to emerge in the early 20th century, when Einstein's theory of relativity introduced time as a dimension bound together with space. With that step, the abstract mathematics of higher dimensions became a framework for understanding physical reality. And so, the 19th century's mathematical leap ended not with a conclusion, but with an opening. It expanded the boundaries of what could be imagined, laying a foundation for physics to build upon. Mathematics worked perfectly well with higher dimensions, but the deeper mystery still waited. Could nature itself be written in more than three? The next chapter of science would take up this question, beginning with the realization that time and space are inseparably joined. At the dawn of the 20th century, physics stood at a crossroads. Newton's laws had reigned supreme for more than 2 centuries, describing the motions of planets and the fall of apples with extraordinary precision. Yet cracks were beginning to appear. The behavior of light, in particular, refused to fit neatly into the old framework. Experiments showed that the speed of light was constant no matter how the observer moved, a fact that clashed with the assumptions of Newtonian mechanics. To reconcile these observations, a new way of thinking was required, one that would change our understanding of dimensions themselves. The breakthrough came in 1905, when Albert Einstein published his special theory of relativity. At its core was a radical idea. Space and time, long considered separate entities, were in fact woven together into a single fabric. Events could no longer be described simply by where they occurred in space. They also had to be located in time, and the two were inseparably linked. This unification gave rise to the concept of space-time, a 4-dimensional continuum in which the universe unfolds. The mathematician Hermann Minkowski, who had once taught Einstein, soon reformulated relativity in geometric language. In a famous lecture in 1908, Minkowski declared that space and time were doomed to fade into mere shadows, and only a union of the two would preserve an independent reality. He introduced the idea of 4-dimensional coordinates, 3 for space and 1 for time, and showed that the equations of relativity could be expressed as simple geometric relationships in this higher dimensional setting. The trajectory of a planet or a particle became a world line traced through space-time, and the speed of light emerged as the ultimate limit, the slope that no world line could exceed. This reimagining of time as the 4th dimension did more than solve puzzles about light. It redefined the very stage on which the universe operates. The geometry of space-time itself became an active player in physics. The passage of time was no longer absolute, as Newton had assumed, but relative to the motion of the observer. 2 clocks moving at different speeds would not agree on the time elapsed, an effect confirmed by precise experiments with fast-moving particles and later with aircraft and satellites. Time dilation, once an unimaginable idea, became an observed reality. Length, too, proved to be relative. Objects moving close to the speed of light contract in the direction of motion, a phenomenon known as length contraction. These effects are not illusions, but consequences of the geometry of space-time. Just as the projection of a 3-dimensional object can appear shorter or distorted when cast onto a 2-dimensional surface, so too does motion through space-time alter perceptions of length and duration. The geometry dictates the outcome, and no observer can escape its rules. In 1915, Einstein expanded his ideas into the general theory of relativity, which extended the union of space and time into a full theory of gravity. Instead of thinking of gravity as a force pulling masses together, general relativity describes it as the curvature of space-time itself. Massive objects like stars and planets bend the fabric of space-time, and smaller bodies follow the curved paths within it. In this view, Earth orbits the Sun not because of an invisible force, but because the geometry of space-time guides it along a curved trajectory. The evidence for this bold idea soon followed. During a solar eclipse in 1919, astronomers observed starlight bending as it passed near the Sun, just as Einstein had predicted. The results stunned the world and confirmed that space-time curvature was more than an abstract notion. It was measurable, real, and fundamental. Decades later, time dilation was confirmed by observing the lifetimes of muons, unstable particles that survive longer when moving at high speeds. The detection of gravitational waves in 2015 by the Laser Interferometer Gravitational Wave Observatory provided yet another confirmation. These ripples in space-time, generated by the collisions of massive objects like black holes, were predicted a century earlier by Einstein's equations. Time as the 4th dimension had moved from a mathematical convenience to a physical reality. Every experiment, every test of relativity, confirmed the picture. The familiar 3 dimensions of space were inseparably bound to a 4th, creating a continuum in which the universe evolves. Our lives, too, are woven into this fabric. Each moment we experience is a slice of a four-dimensional world. Each heartbeat and breath, another step along our world line through space-time. And yet, the recognition of time as a dimension opened a deeper question. If 4 dimensions could be real, why should there not be more? The leap from 3 to 4 was once unimaginable, and yet it became the cornerstone of modern physics. Perhaps higher dimensions beyond 4, long described by mathematics, might also play a role in nature. This possibility would soon inspire new theories that stretched beyond relativity, searching for unification and deeper understanding. The idea that time is a dimension alongside length, width, and height forces us to rethink what it means for events to occur. In everyday life, we imagine the present moment flowing smoothly from the past into the future. Yet relativity shows that this flow is not universal. Different observers moving at different speeds do not agree on the order or duration of events. What one observer considers simultaneous, another may place apart in time. This relativity of simultaneity arises directly from the geometry of spacetime and has been confirmed repeatedly in experiments. One of the clearest demonstrations comes from particle physics. Muons created in the upper atmosphere by cosmic rays should decay within microseconds, too short a lifetime for many of them to reach Earth's surface. But because they are moving at speeds near that of light, time for the muons passes more slowly relative to Earth. Their internal clocks tick at a different rate, allowing them to survive long enough to be detected on the ground. Without time dilation, the observed number of muons would be far smaller. Instead, measurements match precisely with the predictions of special relativity. A similar effect has been measured with atomic clocks. In 1971, an experiment known as Hafel, Keating placed highly accurate cesium clocks on commercial airliners flying around the world. When the clocks were compared with stationary ones on the ground, differences appeared exactly as relativity predicted. The moving clocks experienced less time. Modern versions of this test are performed daily with the satellites of the Global Positioning System. GPS would not function without corrections for both special and general relativity, since the satellites are moving quickly and orbiting in a weaker gravitational field than Earth's surface. These effects cause their clocks to drift relative to those on the ground, and the corrections are essential to keep navigation accurate. General relativity extends these ideas further by linking time to gravity. In a strong gravitational field, time passes more slowly. This gravitational time dilation means that clocks placed at different altitudes tick at different rates. Experiments with atomic clocks raised just a few meters show measurable differences. Near a black hole, the effect becomes extreme. An observer far away might see time nearly freeze for something falling into the black hole, though for the falling object itself, time would continue normally. This effect, though difficult to picture, is a natural consequence of space-time curvature. The concept of space-time curvature has transformed how we understand the universe at large scales. Light traveling near massive bodies follows curved paths, explaining the gravitational lensing observed when distant galaxies are magnified by the mass of intervening clusters. The expansion of the universe itself, described by the solutions to Einstein's equations, is a manifestation of space-time geometry. The redshift of light from distant galaxies is not because the light slows down, but because the very fabric of space-time is stretching. The four-dimensional view also reshapes philosophy. In Newton's picture, time marched forward relentlessly, the same everywhere, a universal stage for events. In relativity, time is part of a block universe, where past, present, and future are all coordinates within space-time. Our sense of the present may be a feature of consciousness rather than of physics. Although debates continue about how to interpret this picture, the evidence leaves no doubt that time behaves as a dimension intertwined with space. The transition from 3 to 4 dimensions was therefore more than a technical adjustment. It revealed a universe far stranger than common sense had imagined. Clocks tick at different rates depending on speed and gravity. Rulers shrink when moving near light speed, and the geometry of space itself is dynamic, capable of bending and rippling. These are not science fiction ideas, but measured realities confirmed by experiment after experiment. The recognition of time as the fourth dimension also prepared the ground for modern theories of the cosmos. Without Minkowski's geometry, general relativity, could not have been formulated. Without relativity, the expansion of the universe, the prediction of black holes, and the detection of gravitational waves would remain unexplained. Time as a dimension is no longer optional. It is the language in which nature speaks. But if physics could incorporate time as a real dimension, then the barrier to more dimensions seemed less absolute. The leap from 3 to 4 showed that what once seemed unimaginable could turn out to be real. As physicists absorbed this lesson, they began to ask whether more dimensions might exist beyond the 4 we experience. Could nature hide extra dimensions in ways that are subtle yet profound? The next steps in physics would be driven by this possibility, beginning with the first attempts to unify the forces of nature using a 5th dimension. The recognition of time as the 4th dimension did not only revolutionize physics, it also reshaped how humanity understands its own place in the universe. The idea that we each trace a path, a world line, through space-time gives a new perspective on existence. Our lives are not isolated moments, but continuous journeys embedded in a 4-dimensional continuum. Every event that has happened, and every event that will happen, can be located in this structure. It is a startling departure from the familiar view of a flowing present, yet it is a view compelled by experiment and observation. The predictive power of relativity confirms that this picture is not just philosophy but physical reality. When scientists plan spacecraft trajectories to distant planets, they rely on the equations of general relativity to account for the curvature of spacetime near the Sun and planets. The tiny adjustments these equations require make the difference between a successful orbit and a missed target. The discovery of the planet Neptune itself was made possible by careful measurements of gravitational effects. And today, the same principles guide robotic explorers across the solar system. Relativity, grounded in the geometry of 4-dimensional spacetime, has become a practical tool. Gravitational lensing, once a prediction, is now an essential method in astronomy. Light from galaxies billions of light-years away is bent and magnified by intervening clusters, allowing astronomers to see further into the cosmos than would otherwise be possible. The pattern of this bending matches perfectly with the mathematics of space-time curvature. In some cases, entire galaxies appear duplicated or stretched into arcs, known as Einstein rings, dramatic visual evidence that space-time is not a rigid backdrop, but a dynamic fabric. The detection of gravitational waves brought this picture into even sharper focus. In 2015, observatories in the United States measured tiny distortions in spacetime caused by the merger of 2 black holes over 1 billion light-years away. The signals matched precisely with predictions from Einstein's equations. For the first time, humanity not only saw the effects of spacetime curvature, but also heard its ripples. These waves confirmed that spacetime is not just a mathematical abstraction, but a medium that can carry energy across the cosmos. All of these discoveries reinforce the central idea that time is a true dimension of the universe, woven with space into a single structure. Our everyday sense of time as a river flowing uniformly is a limited perspective, much as the flat horizon of Earth once misled sailors into thinking the world was bounded. Relativity reveals a deeper reality, one where time can stretch, slow, or curve, depending on motion and gravity. It is not a backdrop but an active ingredient of the cosmos. The philosophical implications remain profound. If time is a dimension, then the universe may be better understood as a whole, 4-dimensional block, with past, present, and future all existing together. Our perception of a moving present could be an artifact of how consciousness navigates this block. While physics cannot yet resolve the full meaning of this picture, it shows how science can reach conclusions that challenge intuition while remaining anchored in evidence. The leap from 3 to 4 dimensions was once unimaginable. For centuries, thinkers assumed that 3 spatial dimensions were all there could be, and that time was something entirely different. Relativity shattered that division and proved that dimensions could extend beyond what the senses reveal. The success of this leap gave courage to imagine further ones. If time could be accepted as a dimension, then perhaps additional spatial dimensions might also be part of reality, hidden from direct observation, but essential for a deeper unification of forces. This is where the story naturally turns next. Having accepted time as the fourth dimension and space-time as the stage for gravity and motion, physicists in the early 20th century began to explore whether more dimensions could explain other mysteries. The first serious attempt came with Kaluza and Klein, who proposed in the 1920s that electromagnetism and gravity could be united by adding a fifth dimension. Their theory was elegant, mathematically consistent, and bold. It did not succeed in its original form, but it opened a new path. The leap to 4 dimensions, once proven by relativity, left science with a tantalizing question. If 4 dimensions are real, could more exist beyond them? Mathematics had already shown the way. The next chapter of physics would take up this challenge, searching for unity in the form of hidden dimensions curled beyond perception, waiting to be revealed. When Einstein's general theory of relativity reshaped physics in the early 20th century, it revealed a universe where gravity was not a force in the Newtonian sense, but the geometry of space-time itself. The triumph of relativity inspired many physicists to ask whether other forces of nature might also be explained geometrically. If gravity could be described as curvature in 4 dimensions, perhaps electromagnetism, and even the other fundamental forces, might emerge from a similar framework. This desire for unification has driven physics for centuries, from Newton's laws that linked the heavens with Earth, to Maxwell's equations that joined electricity and magnetism into a single theory. In the years following relativity, one of the first bold steps toward unification came from a surprising idea: the possibility that the universe contains an extra dimension beyond the 4 of space and time. In 1921, Theodor Kaluza, a mathematician from Germany, proposed that by adding a 5th dimension to Einstein's equations, gravity and electromagnetism could be described within a single framework. His idea was as elegant as it was daring. Kaluza showed that when Einstein's general relativity was extended to 5 dimensions, the equations naturally split into 2 parts. One part described gravity in 4-dimensional spacetime, exactly as Einstein had formulated it. The other part resembled Maxwell's equations for electromagnetism. In one stroke, geometry seemed capable of uniting 2 of the fundamental forces. This unification was breathtaking. The 4-dimensional fabric of spacetime that Einstein had described was expanded into a 5-dimensional continuum, where both gravity and electromagnetism appeared as aspects of geometry. Electromagnetic fields were reinterpreted as the manifestation of curvature in the hidden dimension. In this picture, what appeared in 4 dimensions as separate forces were, in higher dimensions, facets of the same geometric reality. But Kaluza's theory raised a pressing question. If a 5th dimension exists, why do we not see it? Our experience shows only 3 spatial dimensions and 1 of time. Kaluza himself acknowledged this problem, but it was Oskar Klein, a Swedish physicist, who offered a possible solution in 1926. Klein suggested that the extra dimension might be compactified, curled up so tightly that it is effectively invisible to human senses and to experiments. Just as a garden hose looks like a one-dimensional line from a distance but reveals a hidden circular dimension when examined closely, the universe might contain additional dimensions so small that they escape detection. Klein used the tools of quantum mechanics, which were rapidly developing at the time, to argue that the compactified dimension could be on the scale of the Planck length, far smaller than anything observable with current instruments. In such a scenario, particles moving in 4-dimensional spacetime might carry hidden signatures of the extra dimension, detectable only at very high energies. This idea provided a physical mechanism by which extra dimensions could exist without contradicting ordinary experience. The Kaluza-Klein theory, as it came to be known, represented the first serious attempt to incorporate higher dimensions into physics. It showed that the mathematics of relativity could be extended in a natural way, and that such an extension could bring unity to the laws of nature. The elegance of the theory inspired great interest, and for a time it seemed that the path to unification had been found, yet problems soon emerged. The theory successfully combined gravity and electromagnetism, but it did not account for the strong and weak nuclear forces, which had not yet been fully understood in the 1920s. Moreover, attempts to make precise predictions from the 5-dimensional framework led to difficulties. Without experimental evidence, the theory remained speculative. By the mid-20th century, as quantum field theory and particle physics advanced, Kaluza-Klein faded from the center of attention. Still, the importance of the theory cannot be overstated. It marked the beginning of a tradition in modern physics, the search for unification through higher dimensions. Its central idea, that dimensions can be compactified and hidden from view, continues to shape theoretical research to this day. In fact, when string theory emerged later in the 20th century, it revived and expanded upon these very principles, proposing not just one, but several extra dimensions compactified on complex geometric shapes. The Kaluza-Klein model also had profound conceptual influence. It demonstrated that higher dimensions were not just mathematical curiosities, but could play an active role in physical theories. It suggested that the universe might be richer and more complex than what human senses reveal, and that geometry might provide the key to unlocking its secrets. Though the original Kaluza-Klein theory did not succeed in fully unifying physics, it remains a milestone, a bold step that revealed the potential of higher dimensional thinking. It bridged the leap from mathematics to physics, turning abstract ideas about extra dimensions into a serious scientific proposal. Decades later, when string theory rose to prominence, physicists would look back to Kaluza and Klein as pioneers who first dared to extend the dimensional stage on which the universe plays out. The notion of a hidden fifth dimension reminds us that the boundaries of perception are not the boundaries of reality. The familiar four dimensions may be only a shadow of a larger structure, with unseen directions curled tightly beyond our reach. Having accepted time as the fourth dimension, science now entertained the possibility that more might exist, and that they could hold the key to unifying the forces of nature. This realization set the stage for the next revolution, when physicists would discover that consistency in their theories demanded not just one extra dimension, but many more. The Kaluza-Klein proposal arrived at a time when physics was undergoing rapid change. Einstein's general relativity had redefined gravity as geometry, while quantum mechanics was just beginning to transform our understanding of matter and energy. Within this fertile atmosphere, Kaluza's idea that electromagnetism might also be geometric felt both natural and revolutionary. It offered the hope that all forces could be understood as different aspects of space-time itself. The mathematical structure of the theory was strikingly elegant. By extending Einstein's four-dimensional equations into 5 dimensions, Kaluza found that the new equations contained not only the familiar components of gravity, but also terms that matched Maxwell's equations of electromagnetism. What had been 2 distinct sets of laws now appeared as a single unified framework. The 5th dimension acted as the hidden stage where the electromagnetic field lived, while in our 4-dimensional perception, it emerged as a force. The beauty of this result cannot be overstated. The equations did not need to be forced to fit. They fell naturally into place, as if geometry itself had been waiting to reveal its deeper structure. Many physicists were captivated by the possibility that nature was fundamentally geometric, that all interactions could be traced to the shape and curvature of higher dimensional space. Yet the practical obstacles were formidable. One immediate problem was the absence of evidence for a 5th dimension. Unlike time, which revealed itself through relativity's predictions of time dilation and gravitational curvature, the 5th dimension left no obvious trace. Everyday experience offered no hint that another direction existed. Klein's proposal of compactification, published in 1926, sought to resolve this. He imagined the extra dimension curled into a tiny circle, far too small for human senses or even contemporary experiments to detect. Klein's analogy of the garden hose helped illustrate the idea. From far away, the hose looks like a one-dimensional line. Only when viewed up close does the circular cross-section become visible. Similarly, the universe might contain tiny curled dimensions, visible only at scales far smaller than atoms. Particles moving in such a space would have quantized momentum around the compact dimension, producing a spectrum of possible states. These so-called Kaluza-Klein modes represented a concrete prediction of the theory, though they lay far beyond the reach of instruments of the day. This notion of hidden compact dimensions was profound. It offered a way to reconcile the existence of extra dimensions with the apparent four-dimensional world. More importantly, it provided a framework for later theories, especially string theory, which relies on multiple compactified dimensions. Without Klein's insight, the idea of higher dimensions might have remained abstract. With it, physicists had a mechanism that could make extra dimensions compatible with observation. Still, the Kaluza-Klein theory had limitations. It could unify gravity and electromagnetism, but it had nothing to say about the strong and weak nuclear forces, which would only be discovered and understood decades later. The mathematics also produced additional fields that did not correspond to anything observed in nature. Attempts to refine the theory ran into difficulties, and enthusiasm gradually waned. By the mid-20th century, the focus of theoretical physics had shifted toward quantum field theory, particle physics, and the newly emerging Standard Model. And yet, the influence of Kaluza and Klein endured quietly. Their theory demonstrated that higher dimensions could serve as more than mathematical curiosities. They could form the backbone of physical law. Even if the original model did not succeed, the seed had been planted. Later generations of physicists would return to the idea, inspired by its elegance and potential. When string theory emerged in the 1970s and 1980s, requiring additional dimensions for consistency, Kaluza, Klein, compactification provided the template. Beyond its technical contributions, the Kaluza-Klein theory also shaped the philosophical landscape of physics. It suggested that reality might be layered in ways invisible to direct perception. What we call forces could be shadows of higher dimensional geometry. Our senses, evolved for survival on Earth, might reveal only part of the cosmic architecture. The idea echoed the lesson of relativity, that intuition built from daily experience is not a reliable guide to the deeper structure of the universe. In this sense, Kaluza and Klein carried forward the spirit of the 19th century mathematicians like Riemann. They took the leap from abstract geometry to physical law, showing that extra dimensions were not just mental constructs, but possible constituents of nature itself. The fact that their theory could reproduce known physics so neatly lent credibility to the idea that higher dimensions were more than imagination. Though overshadowed in its own time, the Kaluza-Klein theory remains one of the most daring and elegant attempts at unification. It showed that by extending dimensions, the boundaries between forces could blur and merge. It hinted that the ultimate explanation of the universe might be found not in separate categories of gravity, electromagnetism, and nuclear forces, but in a single geometric fabric woven through unseen dimensions. As physics advanced, this vision would be both challenged and revived. The early dream of unification through a fifth dimension did not survive intact, but it left behind a guiding principle. Extra dimensions might be hidden, compact, and difficult to detect, but they could hold the key to the unity of nature. The search for this unity would eventually lead physicists back to higher dimensions, now with the tools of quantum theory and the mathematics of strings and brains. The story of Kaluza and Klein thus marks the first step in a path that continues into the present day. The legacy of the Kaluza-Klein idea is not measured only by the equations it produced, but also by the questions it forced physicists to ask. Could the geometry of space itself hide the secret of unification? Could the forces of nature be explained not as independent entities but as projections of a richer dimensional reality? These questions, once considered speculative, became part of the mainstream conversation in theoretical physics because of Kaluza and Klein's bold proposal. One of the most intriguing aspects of their theory was the way it suggested a layered structure of reality. In 4 dimensions, gravity and electromagnetism appear distinct. In 5 dimensions, they emerge from a common source. This pattern invites a further leap. Perhaps all the forces we know are shadows of a single higher dimensional law. If one extra dimension can unify 2 forces, perhaps more dimensions could unify them all. This line of thought would not bear fruit immediately, but decades later, it became the foundation of string theory and its successors. The compactification mechanism proposed by Klein remains especially significant. By imagining dimensions curled up so tightly that they are invisible at human scales, Klein offered a solution to one of the central puzzles of extra-dimensional theories. His insight foreshadowed the modern concept of Calabi-Yau manifolds, the intricate shapes that serve as the hidden dimensions of string theory. Though Klein could not have anticipated the mathematical complexity of these later developments, his vision of tiny, curled dimensions set the stage. In retrospect, the Kaluza-Klein theory can be seen as both ahead of its time and limited by its era. It was ahead because it dared to extend relativity into uncharted territory, treating electromagnetism as geometry. It was limited because it emerged before the discovery of the nuclear forces and before the development of quantum field theory. Without the full picture of fundamental interactions, the theory could not achieve the unification it promised. As physics advanced, the gaps became too large to ignore, and attention shifted elsewhere. Yet even in fading from the spotlight, the theory left a lasting imprint. Its elegance reminded physicists that beauty and simplicity often point the way toward deeper truths. Its failures reminded them that unification requires more than elegance. It requires consistency with all known phenomena. In this balance between beauty and rigor, Kaluza and Klein's work remains a model of bold but disciplined speculation. The story of Kaluza-Klein is also a reminder of how science progresses. Ideas are proposed, explored, tested, and sometimes set aside, only to resurface in new contexts. What may seem like a dead end in one era can become the foundation for breakthroughs in another. The revival of Kaluza-Klein compactification in the context of string theory is a testament to this. Concepts can outlive the theories that first contained them, carrying forward into new generations of thought. Philosophically, the Kaluza-Klein approach deepens the lesson of relativity. Just as Einstein showed that time is not separate from space but part of a larger whole, Kaluza and Klein suggested that forces themselves may not be separate but geometric aspects of a higher dimensional reality. Our senses divide the world into categories, but the deeper structure may be unified. To glimpse that unity requires stepping beyond the boundaries of perception, guided by mathematics. By the mid-20th century, the focus of physics had shifted to quantum electrodynamics, the Standard Model, and the search to understand nuclear forces. The Kaluza-Klein theory faded into the background, studied mainly by those intrigued by its elegance. But when string theory arose in the late 20th century, demanding the existence of multiple hidden dimensions, physicists looked back and saw Kaluza and Klein as pioneers. Their work had shown not only that extra dimensions were mathematically possible, but that they could unify forces in ways otherwise unimaginable. The first physics of extra dimensions did not succeed in its original form. It did not provide the final unification of nature, but it showed that such a path was possible, and it gave science the courage to continue seeking it. Today, the idea that dimensions might extend beyond the familiar four is central to many of the leading theories in fundamental physics. That intellectual lineage begins with Kaluza and Klein, who dared to extend Einstein's equations into the unseen. As the chapter of Kaluza-Klein closes, the path of higher dimensional physics remains open. Their theory stands as a milestone, the first scientific attempt to move beyond four and into the hidden directions of space. Decades later, string theory would take up this mantle, demanding not just one extra dimension, but six, compactified into intricate forms. The story of higher dimensions was only beginning, and the next step would be a leap into the strange and beautiful world of strings. By the middle of the 20th century, physics had achieved a powerful framework in the form of quantum field theory. The electromagnetic force had been unified with the weak nuclear force, and the strong nuclear force was becoming better understood. Gravity, however, remained separate, stubbornly resistant to integration with quantum mechanics. The Standard Model described three of the forces with remarkable accuracy, but gravity stood apart. Physicists continued to search for a deeper unification, and in that search, an unexpected idea emerged, one that would bring higher dimensions back into focus with unprecedented force. That idea was string theory. The origins of string theory lay not in unification, but in the attempt to explain the strong nuclear force. In the late 1960s, particle physicists faced a puzzle. Experiments at high-energy accelerators revealed a bewildering array of new particles. Mesons, baryons, and resonances seemed to multiply without limit, forming a spectrum that resisted neat categorization. To make sense of these results, theorists sought models that could account for the patterns. One proposal, known as the dual resonance model, imagined particles not as points, but as tiny one-dimensional strings, whose vibrations corresponded to different masses and spins. This string picture turned out to capture key features of the observed particle spectrum. But as quantum chromodynamics emerged as the accepted theory of the strong force, string theory seemed to lose its purpose. It might have faded into obscurity, another abandoned idea, if not for a remarkable discovery. The equations of string theory contained a massless spin 2 particle, a perfect candidate for the graviton, the hypothetical quantum carrier of gravity. Suddenly, string theory was no longer just a model for nuclear forces. It had become a candidate for a quantum theory of gravity, something physicists had been seeking for decades. The mathematics of string theory, however, came with a striking requirement. For the equations to be consistent, strings could not vibrate in ordinary 4-dimensional spacetime. They required additional dimensions. Specifically, the theory worked only in 10 dimensions, 9 of space and 1 of time. This was not an optional feature, but a built-in necessity. Attempts to formulate string theory in fewer dimensions led to inconsistencies and anomalies. Only in 10 did the vibrations of strings behave in a way that preserved the mathematics. The return of higher dimensions was therefore unavoidable. If string theory was to be taken seriously, physicists had to accept that the universe might contain 6 extra spatial dimensions beyond the familiar 3. The challenge, as with Kaluza and Klein, was to explain why these dimensions are not observed in daily life. The answer once again lay in compactification. The extra dimensions, string theorists proposed, are curled up into tiny geometric shapes so small that they remain hidden from view. Unlike the simple circle imagined by Klein, however, string theory required more intricate structures. These were called Calabi-Yau manifolds, 6-dimensional spaces with properties that allow string vibrations to remain consistent. The shape of the compactified dimensions determines the properties of the strings. Just as the vibrations of a violin string produce different notes depending on length and tension, the vibrations of fundamental strings produce different particles depending on the geometry of the hidden dimensions. Electrons, quarks, photons, and perhaps even undiscovered particles all emerge as different vibrational modes. In this way, the zoo of particles described by the Standard Model could, in principle, be unified under the geometry of higher dimensions. The elegance of this framework captivated many physicists. For the first time, there seemed to be a theory that could encompass all forces, including gravity, within a single consistent picture. Moreover, string theory avoided some of the infinities that plagued other attempts at quantum gravity. Its extended objects smoothed out the violent fluctuations that arise when particles are treated as mathematical points. The mathematics suggested that the deep structure of reality might not be particles at all, but tiny strings vibrating in 10 dimensions. Still, the leap to 10 dimensions was daunting. Human intuition, already stretched by the acceptance of time as the 4th dimension, now had to contend with 6 more, invisible and compactified beyond direct reach. To make sense of this, physicists relied on analogies, visualizations, and abstract mathematics. Calabi-Yau manifolds were studied intensively, not only for their role in string theory, but also for their intrinsic beauty in geometry. The interplay between physics and mathematics deepened, with discoveries in each field influencing the other. Yet the promise of string theory came with challenges. Compactification allowed many possible shapes for the extra dimensions, each leading to a different spectrum of particles. This created a landscape of solutions, potentially vast, where different Calabi-Yau shapes corresponded to different possible universes. Finding which, if any, matched our own became a central problem. Without experimental evidence to guide the choice, the theory risked drifting into abstraction. Nevertheless, string theory marked a turning point in the history of higher dimensions. It revived the idea with far greater scope than Kaluza-Klein, demanding not one hidden dimension but 6, and tying them directly to the fundamental properties of matter. It showed that extra dimensions were not a curiosity, but a necessity for consistency, and it offered a vision of unification that was mathematically rich and conceptually bold. As the 20th century advanced, string theory grew into one of the most studied frameworks in theoretical physics. Its implications stretched far beyond the original goal of unifying forces, touching on black hole physics, cosmology, and the deep structure of space-time itself. But even as the theory expanded, one question lingered. Could it ever be tested? Without evidence, the 10 dimensions of string theory remained a tantalizing possibility, beautiful in mathematics, but elusive in reality. The next stage in this story would extend the idea even further. String theory itself came in multiple versions, each consistent, but seemingly distinct. Physicists wondered if these were rival theories or facets of a deeper whole. The answer would come in the 1990s, when a new framework called M-theory revealed that the 5 known versions of string theory were connected, and that they all pointed toward an even higher dimensional reality. The emergence of string theory as a candidate for a unified theory of nature marked one of the most dramatic returns of higher dimensions to physics since the days of Kaluza and Klein. But while the 5-dimensional framework of the 1920s had been a bold extension, string theory demanded something far more radical. It required not just one hidden direction, but 6, and the complexity of those hidden spaces carried profound consequences. The mathematical objects chosen to describe these compactified dimensions were Calabi-Yau manifolds, named after Eugenio Calabi and Xingtung Yau, who developed the geometric properties that made them suitable for string theory. These spaces are not simple loops like Klein's circle, but intricate, 6-dimensional shapes with rich curvature. Their properties preserve the delicate mathematical consistency needed for strings to vibrate without producing anomalies. What makes them remarkable is that they allow supersymmetry, a theoretical symmetry, linking particles of matter to particles of force, to be maintained when dimensions are compactified. Supersymmetry, though not yet observed experimentally, is a central feature of many versions of string theory. Each Calabi-Yau manifold determines the vibrational spectrum of strings, and therefore the kinds of particles and forces that appear in 4 dimensions. This means that the hidden geometry acts like a blueprint for the physical world. Different shapes yield different particle families, different masses, and different interactions. In principle, the universe we observe could be traced back to the specific geometry of its compactified dimensions. In practice, however, the challenge is immense. The number of possible Calabi-Yau shapes is vast, leading to what physicists call the landscape problem. There may be more possible compactifications than atoms in the observable universe, each corresponding to a consistent mathematical solution. Among this multitude, only a small fraction might reproduce the physics we see. This landscape raised difficult questions. Was there a unique geometry corresponding to our universe, waiting to be discovered? Or were there many, each corresponding to a different possible cosmos, with ours just one among them? The answers remain uncertain. Some physicists argue that deeper principles may one day single out the correct compactification, while others suggest that the multitude reflects a broader multiverse. Regardless of interpretation, the existence of this landscape highlights both the power and the challenge of string theory. Even without experimental proof, string theory offered striking insights. One of its most profound contributions has been to the study of black holes. By counting the microscopic states of strings and branes, string theory was able to reproduce the entropy of certain black holes, a result first predicted by Jacob Bekenstein and Stephen Hawking. This calculation provided one of the rare cases where string theory made direct contact with established physics, showing that its framework could illuminate mysteries inaccessible to classical or quantum field theory alone. The consistency of string theory in 10 dimensions also offered a partial explanation for why our universe appears 4-dimensional. If the extra 6 dimensions are compactified to scales near the Planck length, they become invisible at ordinary energies. Only at energies far higher than those reachable by current accelerators could their effects be directly observed. This places them far beyond experimental reach for now, but not beyond theoretical importance. The existence of compact dimensions provides a conceptual framework for why reality appears lower dimensional than it truly island. Another remarkable feature of string theory is the way it unifies particles and forces through vibration. Unlike point particles, which are treated as having no internal structure, strings possess length and can vibrate in different ways. Each vibrational mode corresponds to a particle, and the properties of that particle, such as mass and spin, depend on the details of the vibration. The photon, the graviton, and the particles of the standard model can all, in principle, be described as different notes played by the same fundamental string. This musical metaphor captures the elegance of the idea, though the mathematics is intricate. The recognition that gravity emerges naturally in string theory set it apart from other unification attempts. Many theories tried to incorporate gravity into quantum mechanics, but string theory did so automatically. The massless spin 2 particle that appeared in the equations behaved exactly as the graviton should. This gave physicists hope that string theory could provide a quantum theory of gravity, something that had eluded every other approach. By the 1980s, string theory experienced what came to be known as the first superstring revolution. 5 consistent versions of the theory were discovered, each requiring 10 dimensions, but differing in their details. At first, this seemed like a setback. If only one version of string theory described reality, why were there 5? But the richness of the mathematics and the potential for unification kept interest alive. Physicists around the world devoted themselves to exploring these theories, convinced that higher dimensions held the key to the ultimate laws of nature. String theory's demand for 10 dimensions thus became both its most exciting feature and its greatest challenge. It revived the dream of unification by geometry, offering a framework where gravity, electromagnetism, and the nuclear forces could be understood as manifestations of vibrating strings. But it also raised the profound question of whether such extra dimensions could ever be observed. Without direct evidence, the theory remained tantalizingly out of reach, beautiful in its mathematics, yet awaiting its experimental test. The next stage in the story would bring a surprising twist. The 5 versions of string theory, once thought to be rivals, turned out to be connected in unexpected ways. Dualities revealed that they were not separate theories but different aspects of a deeper framework. This discovery would lead to M theory, an 11-dimensional extension that expanded the vision of higher dimensional physics even further. The rise of string theory in the late 20th century brought higher dimensions from the periphery of mathematics into the heart of theoretical physics. The theory's central claim, that the universe requires 10 dimensions for consistency, was not a matter of choice, but of necessity. Every attempt to formulate the mathematics in fewer dimensions collapsed under anomalies, mathematical inconsistencies, that destroyed the framework. Only in 10 dimensions did the equations hold together, a fact that convinced many physicists that nature itself might be hinting at hidden structure. This insistence on 10 dimensions represented a profound shift in scientific thought. In the 19th century, higher dimensions had been seen largely as mathematical curiosities, explored for their beauty, but with little expectation of physical reality. In the early 20th century, Kaluza and Klein suggested a 5th dimension, but their idea remained on the margins, admired, but not universally embraced. With string theory, however, higher dimensions became unavoidable. If the theory was correct, then dimensions beyond the familiar 4 were not optional speculation, but fundamental elements of the universe. The implications reached far beyond particle physics. In cosmology, theorists began to explore whether the compactified dimensions of string theory might influence the early universe. During the rapid expansion known as inflation, hidden dimensions could have played a role in shaping the distribution of matter and energy. In black hole physics, string theory provided tools for counting the microscopic states that give rise to entropy, offering new insights into one of the most perplexing problems in theoretical physics. In mathematics, the study of Calabi-Yau manifolds and related structures flourished, fueled by their central role in string compactification. The collaboration between physics and mathematics grew deeper, with discoveries in one field driving progress in the other. And yet, the obstacles remained. No experiment has yet revealed direct evidence for the existence of extra dimensions. The energy scales required to probe distances as small as the Planck length, where compactified dimensions might become visible, are far beyond the reach of current accelerators. Predictions about the specific shape of the extra dimensions remain uncertain, with the vast landscape of possible Calabi-Yau geometries offering too many choices. Without clear experimental signatures, string theory exists in a delicate position, rich in mathematical beauty, but awaiting decisive tests. Despite these challenges, string theory reshaped the way physicists think about unification. It suggested that the fundamental building blocks of nature are not point particles, but extended objects whose vibrations give rise to everything we see. It offered a vision where the bewildering variety of particles and forces could be understood as the harmonious notes of a deeper symphony. And it reminded scientists that the universe may be far stranger than intuition suggests, with hidden dimensions curled into spaces beyond perception. By the mid-1980s, enthusiasm for string theory reached extraordinary heights. Conferences overflowed with researchers exploring the implications of 10-dimensional physics. The sense was that physics stood on the brink of a final unification, a theory of everything that could explain all forces and particles in a single framework. While the optimism has since been tempered by the difficulty of experimental confirmation, the conceptual revolution remains. Higher dimensions are no longer an optional speculation. They are central to one of the most ambitious attempts at understanding the universe ever conceived. As the exploration of string theory deepened, another mystery emerged. 5 different versions of the theory existed, each internally consistent and mathematically rich, but seemingly distinct. Were they competitors, with only one describing reality, or were they fragments of a larger whole? The answer would come in the 1990s, when dualities revealed hidden connections among the theories. What once looked like 5 separate frameworks were in fact 5 perspectives on a single deeper theory, one that required not 10, but 11 dimensions. This broader framework came to be called M-theory, and it expanded the vision of higher dimensional physics even further. The journey from Kaluza and Klein's 5th dimension to string theory's 10 dimensions illustrates how science moves from speculation to necessity. Each step builds on the last, guided by mathematics, constrained by consistency, and inspired by the hope of unification. Whether string theory's 10 dimensions are ultimately confirmed remains an open question, but the leap they represent is undeniable. Higher dimensions are no longer the domain of thought experiments and analogies. They are at the center of our best attempt to describe the universe at its deepest level. And so the story continues. From the unification of gravity and electromagnetism in a 5-dimensional framework to the compactified Calabi-Yau manifolds of string theory, the pursuit of hidden dimensions has carried physics ever further from intuition and ever closer to a unified vision of nature. The next chapter reveals how the 5 versions of string theory, once rivals, were woven into a single 11-dimensional picture where membranes and higher dimensional objects play as central a role as strings themselves. By the early 1990s, string theory had established itself as one of the leading candidates for a unified theory of physics. It promised a framework where gravity, electromagnetism, and the nuclear forces could all be understood as different vibrations of fundamental strings. It explained why gravity emerged naturally and why extra dimensions were necessary. But the triumph was incomplete. Instead of one consistent theory, physicists had discovered 5, each mathematically self-consistent, yet seemingly distinct. This situation was unsettling. Nature, after all, should not require multiple incompatible frameworks to describe its fundamental laws. Either one version was correct and the others wrong, or they were all facets of a deeper whole that had yet to be uncovered. The 5 theories shared many similarities. Each required 10 dimensions. Each involved vibrating strings, and each described a spectrum of particles that could, in principle, include the graviton. But they differed in details such as whether the strings were open or closed, the types of symmetries they allowed, and the mathematical structures underlying their equations. For more than a decade, physicists struggled to understand how these pieces fit together. Then, in the mid-1990s, a breakthrough occurred. The breakthrough was the discovery of dualities, deep mathematical connections that showed the five theories were not separate rivals, but different perspectives on the same underlying framework. Dualities revealed that what looked like a weak interaction in one theory could appear as a strong interaction in another. A particle in one framework could appear as a composite object in another. The supposed differences between the theories turned out to be transformations of the same basic structure. It was as if the five roads physicists had been following were in fact different paths through a single landscape. This realization gave rise to what became known as M-theory, an 11-dimensional framework that united the five versions of string theory. The name M was left deliberately ambiguous, sometimes said to stand for membrane, sometimes for mystery, sometimes for mother. The key insight was that strings were not the only fundamental objects. Higher dimensional entities called branes also played a role. A two-dimensional brain, or membrane, could exist in this framework, as could three-dimensional branes and higher. Strings themselves could be viewed as one-dimensional branes. The mathematics required not just 10 dimensions, but 11, with the extra dimension providing room for these extended objects to exist consistently. The introduction of branes expanded the conceptual reach of the theory. Instead of imagining the universe built solely from tiny vibrating strings, physicists now considered vast higher dimensional surfaces. Our entire observable universe, some suggested, might be a three-dimensional brane floating within a higher dimensional bulk. In this picture, all the matter and forces we observe are confined to our brain, while gravity, uniquely, can leak into the extra dimensions. This idea opened new possibilities for understanding both particle physics and cosmology. Branes also offered explanations for puzzles that had troubled physicists. For instance, the relative weakness of gravity compared to the other forces might be explained if gravitational interactions spread out into extra dimensions, while the other forces remained confined to our brain. Though still speculative, such ideas showed the explanatory potential of higher dimensional models. They offered not only mathematical elegance, but possible answers to real physical questions. The unification achieved by M-theory was not a finished theory of everything. Much remained uncertain, including the precise definition of M-theory itself. Unlike the five-string theories, which were mathematically well formulated, M-theory existed largely as a set of relationships and dualities, a framework glimpsed but not fully captured. Physicists could map out its consequences in certain limits, but a complete formulation remained elusive. Even so, the recognition that all five-string theories were facets of a single 11-dimensional structure was a profound step forward. This unification also highlighted a recurring theme in the history of physics. What appear at first to be separate forces, particles, or theories often turn out to be connected at a deeper level. Newton had shown that the same laws govern falling apples and orbiting planets. Maxwell had shown that electricity and magnetism are one. Einstein had shown that space and time are inseparable. Kaluza and Klein had shown that gravity and electromagnetism might be united in higher dimensions. Now M-theory suggested that strings, branes, and multiple string theories were not separate entities, but parts of a larger whole. The move to 11 dimensions represented both a challenge and an opportunity. Human intuition, already stretched to picture 6 compact dimensions in string theory, now had to contend with an even richer structure. Yet mathematics once again provided the tools to navigate this landscape. The equations describing branes and dualities were consistent and powerful, even if their physical interpretation remained difficult. M-theory also inspired new directions in cosmology. If our universe is a brane within a higher dimensional bulk, collisions between branes might play a role in cosmic history. Some models of the early universe explored whether such interactions could trigger inflation or other large-scale phenomena. While these ideas remain speculative and not yet confirmed, they illustrate how higher dimensional frameworks can generate new ways of thinking about the cosmos. The discovery of M-theory marked what physicists call the second superstring revolution. It re-energized the field, showing that the apparent multiplicity of string theories was not a weakness, but a strength, evidence of a deeper unification. The introduction of branes added richness to the framework and opened new paths of exploration. Though many questions remain unanswered, M-theory stands as one of the boldest steps yet in the pursuit of unification through higher dimensions. From Kaluza and Klein's fifth dimension, to string theory's 10, to M theory's 11, the story of physics has continually expanded the dimensional stage on which the universe is understood. Each step has revealed new connections, new possibilities, and new mysteries. The challenge now lies in testing these ideas, in finding evidence that higher dimensions are not only mathematically consistent, but physically real. That quest leads from theory to experiment, from the chalkboard to the collider, as scientists search for traces of extra dimensions in the fabric of the observable universe. The idea that our universe might itself be a brane, a three-dimensional surface embedded in a higher dimensional bulk, represented a profound conceptual leap. In this framework, all of the familiar matter and forces we know would be confined to our brain, electrons, quarks, photons, and the particles of the standard model, would move only within the three spatial dimensions we observe. Gravity, however, would be different. Because it arises from the geometry of space-time itself, gravity could extend into the extra dimensions, spreading through the bulk beyond our brain. This distinction offered a possible explanation for why gravity is so much weaker than the other fundamental forces. While electromagnetism and the nuclear forces are tightly bound to our brain, gravity disperses into hidden dimensions, diminishing its apparent strength in the four-dimensional world we experience. This perspective not only provided a new way of thinking about gravity, but also opened potential experimental avenues. If gravity can leak into higher dimensions, then at very small distances, its behavior might deviate from the familiar inverse square law. Experiments have been designed to test whether Newton's law holds at submillimeter scales, searching for signs of extra-dimensional effects. So far, no deviations have been observed, but the measurements place limits on the possible size of extra dimensions. Each new improvement tightens the constraints, pushing the hidden dimensions smaller and smaller, if they exist at all. The concept of branes also reshaped how physicists thought about fundamental objects. Strings had originally been envisioned as the basic constituents of nature, but M theory showed that strings are only part of a larger family of extended objects. A p-brane, as it is called, can have p spatial dimensions. A zero brane is a point-like particle, a one brane is a string, a two brane is a membrane, and higher branes extend into more dimensions. These branes can carry charges, interact, and even host strings attached to them. The richness of this structure suggested that the true building blocks of the universe might be more varied than anyone had imagined. In certain scenarios, branes offered new insights into black hole physics. Black holes, long a source of mystery, challenged the principles of both general relativity and quantum mechanics. One of the great puzzles, the black hole information paradox, arises from the question of whether information that falls into a black hole is lost forever, in apparent violation of quantum principles. String theory and M theory have provided ways to count the microscopic states of branes that make up a black hole, reproducing the entropy predicted by Bekenstein and Hawking. These results suggest that black holes may not destroy information, but store it in the subtle vibrations and configurations of strings and branes. Though not a complete solution, this work offers some of the most concrete progress yet on the paradox. M theory also brought unexpected connections to mathematics. The study of branes led to new discoveries in geometry and topology, fields concerned with the properties of shapes and spaces. Physicists found that calculations in M theory could solve problems in pure mathematics that had resisted traditional approaches. In turn, mathematical advances deepened the understanding of M theory. This interplay mirrored the earlier relationship between string theory and Calabi-Yau geometry, but on an even grander scale. It highlighted once again the recurring theme that the language of mathematics is not only a tool for describing physics but a partner in discovery. The unification of the five string theories within M theory also carried a philosophical lesson. What had once seemed like competing models turned out to be complementary perspectives. Each version described a different limit of the same overarching framework. This mirrors a pattern throughout science, where progress often comes not from discarding older theories, but from recognizing their domains of validity within a broader structure. Newtonian mechanics, for example, remains accurate at everyday speeds, even though relativity provides a deeper understanding. In the same way, Each string theory remains valid within certain contexts, but all are united under the larger umbrella of M-theory. Despite its promise, M-theory remains incomplete. Unlike string theory, which is defined by precise mathematical equations, M-theory exists mainly as a web of dualities and relationships. Physicists can describe its behavior in certain limits but lack a complete formulation that covers all cases. This incompleteness leaves room for uncertainty. While the theory has inspired many developments, it remains, in part, a work in progress, a glimpse of a deeper reality, still waiting to be fully revealed. The move to 11 dimensions also raises questions about observation. Just as string theory's 6 compact dimensions are hidden from direct experience, M-theory's extra dimension lies beyond current experimental reach. The challenge is to determine whether these ideas can lead to predictions that might one day be tested. For now, the theory provides a conceptual framework rather than a directly verifiable model. But the history of physics suggests that even the most abstract ideas can eventually yield concrete insights. The concept of brains, for instance, has already influenced models of the universe that make contact with observable cosmology. Some versions of brain cosmology propose that the Big Bang might be understood as the result of a collision between brains in higher dimensional space. While such models remain speculative, they illustrate how M-theory provides new ways to think about the origins and evolution of the universe. Even without definitive evidence, the richness of these possibilities demonstrates the power of higher dimensional thinking. As physicists continue to explore the consequences of M-theory, the lessons of history remain clear. Time as the fourth dimension once seemed unthinkable, yet it became the foundation of relativity. A fifth dimension once seemed speculative, yet it opened the path to unification. Now 11 dimensions, populated by strings and brains, may appear far removed from daily experience, but they represent the frontier of our attempt to grasp the ultimate structure of reality. Whether or not M-theory is the final answer, it exemplifies the daring and creativity that have always driven science forward. The unification brought by M-theory reshaped the way physicists think about the fabric of the universe. Instead of a cosmos built only from point particles or even vibrating strings, the picture expanded to include higher dimensional brains as fundamental entities. This broader perspective suggested that reality is not confined to the structures that human senses can picture, but instead is woven from geometric objects that extend into dimensions far beyond perception. The possibility that our universe is itself a three-dimensional brain inside a higher dimensional bulk adds a dramatic new layer to the story. In this scenario, everything we know, galaxies, stars, planets, and life, exists on a brain that floats like a sheet within a larger space. The other dimensions might be vast or compactified, but our access to them is limited. The forces of the standard model, such as electromagnetism and the nuclear interactions, are confined to the brain, while gravity alone can explore the bulk. This picture offers a natural way to explain the weakness of gravity compared to the other forces, and it hints that experiments sensitive to gravitational effects might provide glimpses of extra dimensions. The idea that universes could exist as brains within a larger space also raises intriguing cosmological questions. Could other brains exist parallel to ours, carrying their own matter and perhaps their own versions of physics? If so, interactions between brains might leave imprints on the cosmos we observe. Some models propose that collisions between brains could have triggered the expansion of the universe in its earliest moments. While these ideas remain speculative, they illustrate the imaginative power that higher dimensional frameworks unleash. Brains also enrich the study of quantum gravity. Traditional attempts to merge general relativity with quantum mechanics often run into infinities and paradoxes. By replacing point particles with extended objects, M-theory smooths out many of these difficulties. The surfaces of brains provide new ways for fields and strings to interact, creating structures that remain consistent at the smallest scales. In certain cases, brains have allowed physicists to make calculations about black holes, providing results that align with established predictions of entropy and radiation. These successes suggest that M-theory is not just an abstract idea, but a tool that can illuminate real physical phenomena. Despite its promise, the path forward remains challenging. The mathematics of 11 dimensions is intricate, and a complete formulation of M-theory is still missing. Much of what is known comes from studying special limits, approximations where the equations become tractable. In these corners of the theory, dualities connect different string models and reveal glimpses of the larger structure, but the full picture continues to elude even the most dedicated researchers. This incompleteness is both a source of frustration and of hope, for it means that much remains to be discovered. The philosophical implications are no less profound. Each leap in dimensional understanding has expanded our view of reality, from the unification of space and time to the possibility of hidden curled dimensions, to the sweeping 11-dimensional stage of M-theory. These steps remind us that the universe may be far larger and stranger than we can directly sense. They also show the power of mathematics to guide us where observation cannot yet reach. As with relativity before it, the test will be whether experiments can eventually confirm what theory suggests. For now, M-theory remains a bold framework rather than a finished theory of everything. It provides a unifying vision, showing how strings, brains, and multiple versions of string theory fit into a single structure. It opens new possibilities for cosmology, black hole physics, and the unification of forces. But it also leaves open questions about its precise formulation, its predictions, and its testability. In this sense, M-theory represents both a triumph of imagination and a challenge for the future. The journey from 3 familiar dimensions to 11 abstract ones underscores a central theme of science. The universe does not conform to human expectations. Again and again, reality has revealed itself to be deeper and more complex than intuition suggests. The leap to M-theory may or may not mark the final stage of this process, but it captures the spirit of exploration that drives physics. By daring to imagine hidden dimensions and unseen brains, scientists continue the quest to unify the forces of nature and to uncover the ultimate structure of reality. As the story of M-theory reaches this point, the question shifts from theory to evidence. If extra dimensions and brains are real, how might we detect them? Could high-energy experiments reveal their presence? Or might cosmology provide indirect clues? The search for answers leads us to the laboratories of particle colliders and the observations of the cosmos itself, where traces of higher dimensions may yet be found. The idea of higher dimensions is compelling in mathematics and theory, but science requires more than consistency and beauty. For a theory to become part of physics, it must face experiment. If extra dimensions are real, they must leave signatures in the observable universe. One of the most direct places to search for them is at particle colliders, where protons and other particles are smashed together at extreme energies. Colliders recreate, on the smallest scales, conditions that may have existed fractions of a second after the Big Bang. If compactified dimensions exist, the violent collisions inside accelerators could shake them, producing effects that we can detect. The logic is rooted in how forces behave across dimensions. In a universe with compact dimensions, particles can carry momentum, not only in the familiar 3 directions, but also around the hidden loops of space. To an observer confined to 3 spatial dimensions, these momenta would appear as heavier versions of ordinary particles, stacked in a tower of states, known as Kaluza-Klein modes. Detecting such modes would be clear evidence for extra dimensions. Another possibility is that gravitons, the hypothetical particles of gravity, could escape into the higher dimensional bulk, leaving behind an apparent loss of energy in collider experiments. Some theories also predict that collisions at sufficiently high energy could produce microscopic black holes, fleeting objects that evaporate instantly in a burst of radiation. The largest and most powerful collider built so far is the Large Hadron Collider, or LHC, located near Geneva and operated by CERN. The machine consists of a 27-kilometer ring buried deep underground, where superconducting magnets accelerate protons to nearly the speed of light. When these protons collide, they release energies of trillions of electron volts, conditions intense enough to probe distances smaller than a trillionth of a centimeter. Detectors surrounding the collision points, such as ATLAS and CMS, record the spray of particles produced, capturing data at unimaginable rates. It was at the LHC that the Higgs boson was discovered in 2012, confirming the last missing piece of the Standard Model. But beyond that success, the LHC has also been a tool to search for signs of extra dimensions. Physicists have examined billions of collision events, looking for unusual signatures. One is an imbalance in momentum, as if particles have vanished into invisible realms. Such missing energy events could indicate gravitons escaping into higher dimensions. Another is the appearance of heavy resonances, echoes of Kaluza-Klein excitations. A third is the sudden release of many particles at once, a possible signal of a microscopic black hole forming and evaporating. Each of these effects would be revolutionary, proving that space-time extends beyond the 4 dimensions of experience. So far, none of these signatures have been observed. The data from the LHC place strict limits on the size of extra dimensions, ruling out scenarios where they are larger than a fraction of a millimeter. While this may sound tiny, it is in fact enormous compared to the Planck scale, the realm where quantum gravity is expected to dominate. That such large extra dimensions are excluded is a significant finding, guiding theorists toward models where hidden dimensions are smaller, more curved, or otherwise harder to detect. Each null result narrows the landscape of possibility, refining our understanding of what is consistent with reality. 2 key theoretical models illustrate the possibilities. The Arkani-Hamed-Dimopoulos-Dvali model, proposed in the late 1990s, suggested that extra dimensions could be large enough to alter gravity at submillimeter scales, with only gravitons able to move through them. In this scenario, colliders could produce detectable missing energy events. The Randall-Sundrum model, by contrast, proposed warped extra dimensions, where the fabric of spacetime itself is curved in such a way that gravity appears weak in our brain. Both models make predictions that colliders can test, though neither has yet found experimental support. Future colliders promise to extend the search further. Proposals include machines many times more powerful than the LHC, capable of reaching energies where new phenomena may appear. The Future Circular Collider in Europe and the Circular Electron-Positron Collider in China are 2 such projects under consideration. If built, they would probe deeper into the structure of matter and space, searching for the faint signatures of hidden dimensions. These efforts require international cooperation and enormous resources, but they represent the next step in humanity's attempt to peer beyond the visible. Even in the absence of direct discoveries, collider experiments provide indirect tests. By measuring the properties of known particles with extreme precision, physicists can search for tiny deviations from the predictions of the Standard Model. The Higgs boson, with its unique role in giving mass to particles, is a prime target. Any anomaly in its interactions could signal new physics, perhaps influenced by higher dimensions. Similarly, the behavior of heavy quarks, rare particle decays, and subtle asymmetries all provide opportunities to detect indirect evidence. These measurements require vast amounts of data, but colliders continue to deliver, pushing precision to new frontiers. The search for extra dimensions at colliders exemplifies the interplay between theory and experiment. Theorists build models that predict observable effects. Experimentalists design detectors to test them, and the cycle repeats. When no evidence appears, models are refined or discarded. When hints arise, they are tested against new data. This iterative process is the strength of science, ensuring that only ideas consistent with nature survive. It also illustrates the humility of physics. The mathematics of higher dimensions is beautiful, but beauty is not proof. The universe may or may not contain hidden dimensions, and only evidence can decide. Colliders have not yet revealed them, but they have mapped the boundaries of possibility with extraordinary precision. The search continues, driven by both curiosity and the recognition that the stakes are profound. If colliders ultimately fail to detect extra dimensions, the quest will not end. The cosmos itself is a natural laboratory, with energies and scales far beyond human machines. The patterns of the cosmic microwave background, the behavior of dark matter and dark energy, and the ripples of gravitational waves may all carry the signatures of higher dimensions. When experiments on Earth reach their limits, the sky itself becomes the next arena. When colliders on Earth reach their limits, the cosmos itself becomes the laboratory. The universe operates on scales and energies far beyond what humans can reproduce, offering natural experiments in the physics of higher dimensions. From the afterglow of the Big Bang to the structure of galaxies, from the nature of dark matter to the acceleration of cosmic expansion, clues may lie hidden in the sky. If extra dimensions exist, they may leave imprints not in machines but in the fabric of the universe itself. One of the richest sources of information is the cosmic microwave background, the faint radiation left over from the early universe. This light, released when the cosmos was about 380,000 years old, carries subtle patterns of temperature and polarization across the sky. These patterns record the seeds of galaxies and the fingerprints of fundamental physics. If higher dimensions influenced inflation, the rapid expansion that smoothed and stretched the early cosmos, their effects might still be visible in this radiation. Tiny deviations from the expected spectrum or unusual correlations between regions of the sky could signal the presence of hidden dimensions. So far, observations by satellites such as WMAP and Planck have matched the predictions of standard cosmology with striking precision, but the door is not closed. Future experiments aim to push sensitivity further, searching for the faintest signatures of primordial physics. Dark matter is another frontier where higher dimensions may leave a mark. Though invisible, dark matter reveals its presence through gravity, binding galaxies together and shaping the large-scale structure of the cosmos. Its nature remains unknown, but some theories link it to extra dimensions. In models inspired by Kaluza-Klein theory, dark matter could consist of the lightest stable particle in the tower of excitations that arise from compactified dimensions. Such a particle would interact weakly with ordinary matter, fitting the profile of dark matter candidates. Experiments deep underground, in space, and at colliders all search for signs of these particles, but none have yet been found. Each new null result narrows the possibilities, refining the link between dark matter and extra dimensions. Dark energy, the mysterious force driving the acceleration of cosmic expansion, also invites speculation about hidden dimensions. Some models propose that the geometry of extra dimensions influences the vacuum energy of space, producing the effect we observe as dark energy. Others suggest that the leakage of gravity into higher dimensions alters cosmic dynamics on large scales. These ideas remain unproven, but they highlight how higher dimensions could shape not only microscopic physics, but the fate of the universe itself. Inflation, the exponential growth of the universe in its earliest fraction of a second, offers another testing ground. Many inflationary models are inspired by higher dimensional physics, where scalar fields arise naturally from the geometry of compact spaces or the positions of branes. Collisions between branes in the early universe have been proposed as triggers for inflation, leaving possible signatures in the cosmic microwave background. While these models are speculative, they illustrate the deep connections between cosmology and the mathematics of extra dimensions. Gravitational waves provide a newer window. These ripples in spacetime, first detected in 2015, carry information about violent events, such as black hole mergers. In principle, they could also reveal properties of spacetime itself. If gravity propagates into higher dimensions, gravitational waves might disperse or lose energy in ways that differ from predictions of general relativity. Current observations match Einstein's theory with impressive accuracy, but future detectors, both on Earth and in space, will test these ideas more stringently. Subtle deviations could signal the presence of hidden dimensions. The large-scale structure of the universe also offers tests. The distribution of galaxies across billions of light-years reflects the growth of matter under gravity. If gravity leaks into higher dimensions at large scales, the pattern of clustering might deviate from expectations. Surveys mapping millions of galaxies are already testing these ideas, and future instruments will sharpen the picture. The universe itself is the largest experiment possible, and its structure encodes the laws of physics across cosmic time. Despite these opportunities, no direct evidence has yet emerged. The cosmic microwave background shows no anomalies demanding higher dimensions. Dark matter remains elusive, with no detection confirming Kaluza-Klein particles. Dark energy is still a mystery, with no model definitively linking it to hidden dimensions. Gravitational waves match Einstein's predictions, and galaxy surveys align with standard cosmology. These results do not rule out higher dimensions, but constrain how they can exist. If they are real, they must be subtle, influencing physics in ways that are consistent with all we observe so far. This outcome reflects both the power and the humility of cosmology. The universe is vast and ancient, offering countless tests of physics, but interpreting its signals is complex. Noise, astrophysical processes, and observational limits all complicate the search. Yet the pursuit continues, driven by the recognition that the cosmos may hold answers beyond the reach of colliders. In the interplay of light, gravity, and structure, the fingerprints of higher dimensions may yet be found. The search for clues in the universe connects directly to the philosophy of science. It reminds us that evidence is not always direct, that sometimes it comes from the patterns of the whole rather than the behavior of parts. It also reminds us that the absence of anomalies is itself a result, narrowing the space of possibility. Whether higher dimensions exist or not, cosmology shows that they must conform to the universe we see, a universe where stability, structure, and life are possible. From the vastness of space to the smallest scales of matter, the question of dimensions weaves through every corner of physics. The cosmos may conceal hidden directions, but it also reveals the fragility of perception. To move from science to philosophy is to confront this fragility directly, to ask whether dimensions are discovered realities or human inventions, and what it means to know them at all. The scientific study of dimensions inevitably leads to philosophy, for the very concept of a dimension lies at the boundary between mathematics, perception, and reality. A dimension is at once a practical tool for measurement, a property of equations, and a feature of existence. But are dimensions discovered in nature or invented in thought? Do they exist independently of us, or are they frameworks our minds impose to make sense of the world? These questions reach beyond physics, touching on metaphysics, epistemology, and the limits of human cognition. In everyday life, we experience three spatial dimensions: length, width, and height, and a flow of time. Our language and intuition are shaped by these. We speak of moving forward, turning left, climbing upward, or waiting for time to pass. There are no words for directions beyond these three, for our bodies and senses are confined to them. When physicists introduce higher dimensions, they rely on mathematics, using coordinates and symbols that stand in place of experience. The very need for abstraction reveals a philosophical tension. We cannot imagine these dimensions directly, yet we can describe them rigorously. This tension has long fascinated philosophers. Immanuel Kant argued in the 18th century that space and time are forms of human intuition, structures through which we perceive reality, rather than properties of reality itself. If Kant is right, then higher dimensions may be forever beyond us, not because they do not exist, but because human minds are not built to perceive them. Henri Poincaré, a century later, suggested that geometry is a convention, chosen for its usefulness, rather than discovered as truth. From this perspective, higher dimensions are not realities waiting to be seen, but tools for organizing thought. Yet history complicates these views. Non-Euclidean geometry was once dismissed as an abstraction, but it became essential to general relativity. Time was once thought separate from space, but relativity fused them into space-time. What was once unimaginable became real through evidence. This suggests that higher dimensions, though currently abstract, could one day join the roster of physical realities. Philosophy here acts as a reminder. The boundary between invention and discovery is porous, shifting as evidence accumulates. The The human struggle to visualize higher dimensions has inspired allegories. Edwin Abbott's Flatland remains the most famous, depicting a two-dimensional world whose inhabitants cannot conceive of height until a sphere passes through their plane. To them, the sphere appears first as a point, then as a growing and shrinking circle. The story illustrates how beings bound to lower dimensions may misunderstand higher ones. By analogy, we too may be like Flatlanders, blind to directions beyond three yet surrounded by them. The tale resonates philosophically, suggesting humility before the unknown. This humility shapes modern philosophy of science. Some argue that reality will always exceed human imagination, that mathematics may describe structures we cannot picture. Others note that science has a history of expanding imagination, teaching us to conceive what once seemed impossible. The leap from flat Earth to round, from absolute time to space-time, from 3 dimensions to 4, each was once inconceivable. Perhaps the leap to more than 4 will one day be equally natural. The status of dimensions also raises questions of ontology, the study of being. Are dimensions fundamental properties of reality, or are they emergent from deeper structures? Some philosophers suggest that dimensions are not things but relations, ways of describing how objects interact. Others argue that they are as real as matter and energy, woven into the fabric of the cosmos. The debate reflects broader questions about the nature of mathematics itself. Is it discovered, describing realities independent of us, or invented, a creation of the human mind? Beyond epistemology, dimensions touch on meaning. If higher dimensions exist but remain forever beyond perception, what is their significance for human life? Do they change our understanding of purpose, of place in the cosmos, of what it means to know? Some thinkers suggest that contemplating higher dimensions expands the human spirit, showing that reality is larger than daily experience. Others caution against overreach, warning that speculation without evidence risks slipping into imagination without anchor. The balance between wonder and rigor is delicate, yet essential. Culture plays a role here as well. Science fiction and art often blur the line between philosophy and science, using higher dimensions as metaphors for transcendence or horror. Lovecraft's tales of beings from beyond human dimensions evoke fear of the incomprehensible. Other works imagine higher dimensions as pathways to freedom, faster travel, or contact with advanced intelligence. Philosophy recognizes these cultural uses as meaningful, even if they are not scientific, for they reflect how deeply the idea resonates with human thought. Ultimately, the philosophy of dimensions is not about settling the question of whether they exist, but about clarifying what the question means. To know a dimension may mean to measure it, to perceive it, or to describe it mathematically. Each definition carries assumptions and limits. Science seeks evidence, mathematics seeks consistency, and philosophy seeks meaning. Together, they remind us that higher dimensions are more than technical problems. They are windows into the nature of knowledge itself. The dialogue between physics and philosophy ensures that the pursuit of higher dimensions is not only about equations but also about human understanding. It highlights the fragility of perception, the creativity of mathematics, and the humility required in science. Whether or not higher dimensions are ever observed, the act of asking about them deepens our grasp of reality, and it prepares us to see how culture and imagination have embraced these ideas, shaping the way societies think about space, time, and the unknown. Long before physics demanded extra dimensions for mathematical consistency, human imagination was already exploring them. The idea of realms beyond ordinary perception has inspired writers, artists, and philosophers for centuries, serving as both metaphor and speculation. Higher dimensions appear not only in textbooks and theories, but also in novels, paintings, films, and cultural myths. They symbolize transcendence, the unknown, and the possibility that reality is richer than it seems. By following how imagination has embraced higher dimensions, we see how culture prepares the ground for science, giving language and imagery to what mathematics describes in abstraction. One of the earliest and most influential treatments of extra dimensions came in Edwin Abbott's Flatland, published in 1884. The story depicts a two-dimensional world where inhabitants can perceive only length and width. Their rigid society reflects Victorian hierarchies, but its enduring power lies in the allegory of perception. When a sphere from the third dimension enters flatland, its passage is experienced as a point that grows into a circle and shrinks again. To the flatlanders, the idea of height is unthinkable until it is demonstrated. The story suggests that our inability to visualize higher dimensions may not prove their absence, only our limitation. Flatland became a classic, inspiring countless adaptations and remaining a teaching tool in physics classrooms today. As science fiction developed in the 20th century, higher dimensions became a natural canvas for storytelling. Writers imagined hyperspace as a realm through which faster-than-light travel might be possible, bypassing the restrictions of relativity. Though speculative, hyperspace became a staple of the genre, appearing in works from early pulp adventures to modern franchises like Star Wars and Star Trek. In these tales, higher dimensions are not abstractions, but practical tools for exploration, symbols of freedom, and escape from cosmic distances. Other writers used extra dimensions more philosophically. H.P. Lovecraft invoked them as sources of cosmic horror, suggesting that beings from higher dimensions would appear grotesque and incomprehensible to us, their forms distorted by our limited perspective. Madeleine L'Engle, in A Wrinkle in Time, used the concept of tessering folding space through another dimension as a metaphor for love, courage, and transcendence. Jorge Luis Borges wove labyrinths of infinite structure into his stories, hinting at dimensions beyond comprehension. In each case, higher dimensions symbolized realities beyond human control, whether terrifying or enlightening. Visual art also engaged with the idea. In the mid-20th century, Salvador Dali painted Crucifixion, Corpus Hypercubus, depicting Christ on a tesseract, the unfolding of a four-dimensional cube into three-dimensional space. The work challenges viewers to see beyond ordinary perspective, using geometry as a vehicle for spiritual transcendence. Modern digital artists have continued this tradition, creating rotating projections of four-dimensional shapes that visitors can experience interactively. Though we cannot perceive higher dimensions directly, art provides analogies that stretch the imagination. Cinema has played a particularly powerful role in shaping popular views of higher dimensions. In Christopher Nolan's Interstellar, the climax places the protagonist inside a tesseract, where time appears as a physical dimension that can be navigated. Though simplified, the scene draws directly from physics concepts of space-time and higher dimensional geometry, making abstract ideas accessible to millions. Films such as Contact, based on Carl Sagan's novel, depict travel through wormholes, another concept inspired by higher dimensional models of space-time. Even superhero films like Doctor Strange portray folding, twisting dimensions as metaphors for unlocking hidden realities. Though not scientifically literal, these portrayals help audiences imagine possibilities beyond the visible world. Education often draws on culture to explain higher dimensions. Teachers use Flatland to introduce the concept of dimensions beyond perception. Animations of rotating tesseracts show how projections shift in three dimensions, much like shadows reveal shapes in lower ones. These cultural metaphors allow students to grasp ideas that would otherwise feel impossibly abstract. They demonstrate how imagination and science support each other, each offering tools the other lacks. Yet cultural portrayals also blur boundaries, creating both inspiration and confusion. Hyperspace travel and higher dimensional beings make compelling narratives but are not supported by evidence. For the public, it can be difficult to separate metaphor from science. Scientists and educators must clarify that, while imagination inspires, only experiment confirms. The balance between wonder and rigor ensures that fascination with higher dimensions enriches society without misleading it. Still, the enduring cultural fascination reveals something fundamental about human nature. We are drawn to what lies beyond reach, to the idea that reality hides unseen depths. Higher dimensions serve as symbols of mystery and possibility, embodying the hope that there is more to the universe than we can perceive. They inspire both awe and unease, reminding us that the unknown can be both a source of fear and a wellspring of discovery. In this way, culture and imagination do not compete with science but accompany it. They prepare minds to accept ideas that might otherwise seem absurd. They provide metaphors and stories that bridge the gap between mathematics and experience. And they ensure that the search for higher dimensions is not confined to laboratories and equations, but is part of the shared landscape of human wonder. Whether hidden dimensions exist or not remains one of the greatest open questions in science. If they are ever confirmed, they will revolutionize our understanding of reality. If they are not, their pursuit will still have enriched mathematics, culture, and philosophy, leaving us with a deeper appreciation of why 3 dimensions are so uniquely suited to life. Either way, the journey into higher dimensions reflects the human desire to reach beyond the visible, to imagine what lies unseen, and to accept that reality may be larger and stranger than we know. The question, what if space has more than 3 dimensions, is not simply about geometry or physics. It is about imagination, humility, and the recognition that our perspective is limited. In seeking the answer, we discover not only the possibilities of the universe, but also the nature of ourselves, creatures bound to 3 dimensions, yet forever reaching beyond them in thought.